So now we will talk about the photon gas. Right. Well, to start with, we do know that photons have zero rest mass, and so they can be created and destroyed. And as a result, the number of photons is not conserved. A direct consequence of this fact is that the chemical potential mu for photons is equal to 0. Now, you see, this thing can also be seen as follows. From thermodynamics, we have, you see, this relation dE equal to T ds minus P dV plus mu dN. Now let me just follow the same old equation number that we have been following in our last class, continuation. So following that, this equation number will be 92. Okay, now what is S and N? Well, S is the, and as I was saying, S is the entropy and capital N is the number of particles. Now for fixed energy and volume, the photons are created such that, so photons created such that S is maximum. What does this mean? This means that del S, del N or constant EV equal to minus mu by T equal to 0. So this means that mu is equal to 0. This is equation 93. So this means that a photon gas in thermal equilibrium has zero chemical potential. Okay. Now for photons, we have Gs is equal to 2, V is equal to C, and E is equal to P into C. So the number density of photons from P to P plus dP, how much is this? This is basically given by this relation. This we have already discussed previously. So equation 94. Now, as I have already mentioned that for photons we have P is equal to h nu by C. So the number of photons or number density of photons between nu and nu plus d nu, this is basically, just we make a small change and the result is this here. So instead of P term, now we have nu term. This is equation 95. So what about the energy density? So energy density per unit frequency, and this is then given by this relation U nu is equal to N nu H nu, and this is equation 96. Fine. So you see the total energy density. So this was energy density per unit frequency. Now let us talk about total radiation energy density. What do? We do the integration from 0 to infinity for all frequencies, and upon doing that we will get this relation. You see, just doing the integration, equation 97, where we have used x as h nu by kb into t. Now this last integral, this has a value of pi to the power 4 by 15. You can check this yourself. And as a result, we have, you see, this relation finally. So energy density of radiation A T to the power 4, equation 98, where this A is equal to 8 pi by 5 kb to the power 4 divided by hc whole cube, and this has a value of 7.565 into 10 to the power minus 16 joule per Kelvin to the power 4 and per meter cube. Now as a result, the radiation pressure or basically the pressure exerted by photons is then given by what? You remember our visual theorem? There we discussed, since we are talking about relativistic systems, so this is just 1 by 3 into UR, or 1 by 3 into A T to the power 4. So we have derived the relation for radiation pressure. So this is because this 1 by 3 is because photons are ultra relativistic or extreme relativistic, right? ঠিক আছে, কোনো প্রশ্ন থাকলে বলো। Now let's again talk about the transition. So you see, if we have a mixture of ideal gas and radiation, then we will have P gas plus P radiation, right? So this is equal to rho by mu mp kbt plus 1 by 3 A T to the power 4, equation. We don't have to write this now. Now you see, at low temperature the gas pressure, this one dominates, low T, whereas this one dominates at high temperature. Of course you can see from the temperature dependencies of them. Now these two contributions become equal, so P gas equal to P rad. This becomes equal when you can equate both of them, and from there we will get this relation. You see, rho is equal to T by 3 into 10 to the power 6 cube kg per meter cube. Now one can easily show that at the center of the sun, it is basically the gas pressure which dominates over the radiation pressure. You can check this yourself as well. So after that, let me talk a little bit about radiation pressure in stars. Now you see, from equation 68, basically
T is equal to rho c kb T c
yes,
by
yes,
mu
yes,
mp.
right, good. So equation 68 was basically the central pressure, this expression, or m by r cube kb Tc divided by mu into mp. So this was equation 68, right? So you see, from this equation we already know that the central temperature, so from this we have Tc approximately equal to or this is proportional to m by r, right? While what about the central gas pressure? Well, gas pressure is approximately equal to g m square by r to the power 4, right? Now, so the central radiation pressure, it becomes, you see, PR equal to 1 by 3 A Tc to the power 4. This becomes equal to proportional to m to the power 4 by r to the power 4. So ratio of gas pressure to radiation pressure How much is this? This is, you see, করো তোমরা এটা করে দেখো কি হচ্ছে। How much is this? This is proportional to m square. So I am basically writing in a different way. So it is basically radiation by gas pressure, and this shows that radiation by gas is proportional to m square. So what does this mean? This means that the radiation pressure increases as the mass of the star increases. Therefore, the radiation pressure is much more important in massive stars than in low mass stars. Loosely speaking, we can say that radiation dominated materials are much more difficult to confine gravitationally. In fact, you see, very massive stars are dominated by radiation pressure. Stars dominated by radiation pressure. And in fact, stars more massive than 100 solar masses, they are known to be unstable. They are in fact unstable to perturbations. And this imposes an upper limit on stellar mass. Now we will come to this upper limit part in a separate class as well, but this is just, I have given you a very basic idea about how to talk about the upper limit for stars. Now there is something again related stuff as well. You must remember that we discussed previously that for a classical relativistic gas of particles, what did we have? You remember we observed that E total is equal to 0. This result we obtained from the virial theorem. You remember this? And as a result, you can say that the star is marginally bound.
স্যার একটা ফাই এর ভ্যালু ছিল 3 হয়ে গিয়েছিল,
হ্যাঁ হ্যাঁ হ্যাঁ, ওইখান থেকে জিরোটা পেয়েছিল।
ওই ওটাকে লেস দ্যান 3 হতে হয়, তাহলে বাউন্ড হয় স্টারটা।
হ্যাঁ, এইখানে তোমার 3 হয়ে যাওয়ার জন্য এটা মার্জিনালি বাউন্ড হচ্ছে। ওকে, দিস ইজ দ্য রিজন, ইউ সি দিস মার্জিনাল বাউন্ড যে হচ্ছে, দিস ইজ দ্য রিজন আমরা বলতে পারি যে স্টার্স ডমিনেটেড বাই রেডিয়েশন প্রেশার are unstable. কেন? Dominated by radiation pressure means there will be more and more photons, which are energetic in the star, and photons are relativistic system. So you can say this is relativistic gas, and this is what you can say in this way, that stars are marginally bound for radiation dominated stars, right? So if there are no more questions, let us now talk about, so we talked about the photon gas, now we will talk about the electron positron pair gas. Now to start with, you must remember this expression. Remember this we talked about when we talked about the finite temperature electron gas. So this was the relation for pressure, non-degenerate versus and degenerate, and this was equation, some equation was there, I am not writing it down anyway. Okay, now you see this formula for pressure of electron gas has a very wide range of applicability. We discussed this. Now, you see, in reality there is no limit at very low densities. And at very high densities, the only correction required is in the evaluation of the mean number of nucleons per electron. And what happens at the low temperature? Now at very low temperature, gas is no longer fully ionized, and again the evaluation of the number of nucleons per electron becomes complicated. At high temperature, you see, when kBT is greater than equal to mc square, we have relativistic electrons. Now it becomes energetically possible to form electron-positron pairs, that is to create new particles in that case for very high energies. Now we have to write down the distribution functions for not only the electrons but also the positrons as well. Remember, as one is the antiparticle of another, their chemical potential will differ by 2 rest mass energies. And we have, you see, this relation. So, I am writing down the chemical potential of them. And what about the average number of particles? So, this is chemical potential and average number of particles per unit cell. What is it? This is basically, again, very similar to the previous result. Previously we talked about only this one. Now we have just the same relation but with the changed value of the chemical potential. And as a result, you see the number density is given by, for both of them, let me write down the number density. How does it look like? You see, you will see again they are quite similar to each other. You see, just this mu change, where the negative sign corresponds to electron and the positive sign corresponds to positrons respectively, right? Now there is a constraint, however, on the total number of particles, as the difference between the number density of the electrons and positrons must be equal to the number of electrons that came from ionizing all the ions. Okay, so this means that, you see, we have Ne equal to Ne minus minus Ne plus, and this is equal to rho mu E mp. Of course, mu E is equal to 2 by 1 plus x. This we derived previously as well, where x is the hydrogen abundance by mass fraction. Now, given the distribution functions, we may calculate the electron pressure and the electron energy density. However, note that for electron energy density, we shall include not only the kinetic energy of all electrons and positrons, but also the annihilation energy of all electron-positron pairs, but not the rest mass energy of the original electrons. Let me write it down. So, the relation is like this. Electron pressure, it is this, you see, the two contributions, electron, okay, and positron. What about the energy density? This is the expression for energy density. Now, as usual, you see the integrals are quite complicated to evaluate them analytically, but there are simple limiting cases which can be considered, just as we have done previously. Okay, now first we will consider a case of relatively low temperature and low density. So low T and low rho, such that mc square is much greater than E minus mu, much greater than kBT. So this is just like your old Maxwell-Boltzmann distribution. However, we will look for a small correction in order to estimate the number of pairs. So in this approximation, we have this relation. And therefore, the number density of electrons and positrons can be calculated. So, because of this, the number density of electrons and positrons. What about it? Let us write it down. So, for electrons, first let me write here, and this is equal to basically, right, this number. Okay, so now for the positrons, and the result is the following. This is the result. Finally, you see, the number ratio is just what we will expect from a Boltzmann distribution. You will see, it is very interesting. Here, so this is the number ratio, and this corresponds to basically the Boltzmann formula, right? Now it is obvious how to calculate small corrections to electron pressure and electron energy density. It is important to note that the corrections to energy density are relatively larger than the corrections to pressure. Why? This is because the rest mass energy of a small number of pairs is much larger than their thermal energy. Now, so we consider one example. Let us consider another example. So another case let us consider. So case 2. So this was case 1 that we discussed here, number density of electrons and positrons, and we just calculated, you see, for electrons this is the number density, for positrons this is the value, and then the number ratio, we did that, and you see the result is surprising. What is this? This is just the Boltzmann formula. Okay, so now let me consider the second case, which is when kBT is much greater than mc square, and therefore most electrons and positrons are ultra relativistic. Okay, and having the velocities proportional to c. And so what about the energies? The energy is approximately Pc, which is again much greater than mc square or mu. Now in this limit, what we will have is the following. You see, so in this case we will have these numbers much greater than any, which means that there are many more pairs. So many more pairs than original electrons. Okay, so what about the energy density? Now the energy density due to all these pairs, let us calculate this, and you will see that the result is quite surprising. See, so this is the energy density due to all pairs. Here we have substituted x is equal to Pc by kBt, and again this last integral value here, this has a value of 7 pi to the power 4 by 120, and UR is basically our radiation energy density. So I have written this in terms of radiation energy density. Now as the pairs are ultra relativistic, in this limit, you see their thermodynamic properties are very similar to that of radiation. In particular, you see the relation okay. So we have a very interesting application, and now let me talk about the transitions. Well, I have already talked about various transitions previously, but let me just recapitulate this. So the first transition is between radiation and radiation region and ideal gas region. So transitions in equation of state, rho t plane. So radiation region and ideal gas region. Now for that what we do is this, we equate this, P radiation is equal to P gas. এর মানে কি? এর মানে আমি এইভাবে লিখতে পারি 1/3 8 e to the power 4 is equal to kb b into mu rho t. So this means I can write t cube by rho is equal to 3r by a mu, right, where R is equal to kb by mu p. Okay, so এইখান থেকে আমি কি পাচ্ছি দেখো, from here I am getting that t by rho to the power 1/3 is equal to 3.2 into 10 to the power 7 mu minus 3. So we have basically a line, this one, consider this. So basically we have a line with slope 1/3 in log t log rho plot. Okay, now next let me consider the ideal gas region, and তোমরা বুঝতে পারছো তো, non-relativistic degenerate electron gas region. Again for this what we do is P of ideal gas, we equate this to P in the non-relativistic case for electrons. Okay, and what do we get? As a result, we will have here R by mu rho into T is equal to K non-relativistic divided by rho by mu E. to the power 5 by 3. Okay, so this means that T by rho to the power 2 by 3 is equal to mu K n R divided by R into again mu E to the power minus 5 by 3, and this value is 1.21 into 10 to the power 5 mu E to the power minus 5 by 3. So what does this mean? This means that we have a line with slope 2 by 3 in the log t log rho plot. I will finally show you this. Again, another interesting point is, so when degeneracy occurs, কখন? Of course, this happens when your ideal gas, this gas pressure is less than PENR. So from this relation we can say that this happens for rho. You see, from this relation we can say that degeneracy occurs when rho becomes greater than 2 into 10 to the power minus 8 t to the power 3 by 2. This is very important, this relation, the occurrence of degeneracy condition. Okay, next we have number 3, which is the non-relativistic, degenerate region and relativistic degenerate region. Okay, so basically what we have is PF approximately equal to MEC, or X is equal to PF by MEC equal to 1. Now from equation 75 in the text that we did, we already know from this, since X becomes equal to 1, so we have rho is equal to just rho 0 into mu E, and if you do the calculation you will find that this is just 9.8 into 10 to the power 5 mu E gram per centimeter cube. So a constant line. Again we will show this in the density temperature plot. Now the fourth one. So this is again ideal gas region and extreme relativistic degenerate region. So again for that we do this ideal gas equal to PE. So from here we have R by mu rho into T equal to K ultra relativistic rho by mu E to the power 4 by 3. So this means T by rho to the power 1 by 3 is equal to K UR by R mu into mu E minus 4 by 3. This is 4. A value ta koto? It has the value of 1.5 10 to the power 7 mu E to the power minus 4 by 3. Now we note that we are using the CGS units. So what does this mean? This again means that we have a line with slope 1 by 3. Okay, so we have talked about the 4 transition regions. Let me now show you this in plot. So your question is, why do we call it transition, right? Now you can see on the screen. So basically we are talking about how we have talked about the various cases, right? We have talked about ideal gas, radiation, again degenerate gas. We consider 2 limits, non-relativistic and ultra-relativistic or extreme relativistic limit. Now you must be considering that we have got so many cases. Now if we plot them in this temperature density plot, then which part will be dominated by which pressure, right? This is what comes to mind. So this is what I am showing you right now. So you see the equation of state for a gas of free particles in the log T log plane, and I will be now showing you the various dashed lines, which are basically the approximate boundaries between regions where radiation pressure, ideal gas pressure, non-relativistic electron degeneracy and extreme relativistic electron degeneracy dominate. Remember, when I am talking about non-relativistic and extreme relativistic cases, I am talking about the T is equal to 0 approximate cases, right? Finite temperature case will be a little bit different. Now I am showing this for a composition of, say, x is equal to 0.7, z is equal to 0.02. So basically solar composition. So this was the plot, and these are the 4 lines. And you remember how many cases we discussed. Right now we want to explore the transition region or the boundary region. Now you can see 4 red lines or 4 boundaries, and you must remember that we just now discussed these 4 regions. So let me talk about the first one, radiation versus radiation versus ideal gas region. You see, this is the relationship we obtained, or basically a slope of 1/3. Yes, this is the case for radiation and ideal gas boundary. The next one is ideal gas and
Hello sir.
হ্যাঁ বলো।
দেখা যাচ্ছে না, আপনার সাথে কথা কেটে কেটে যাচ্ছে মাঝে মাঝে।
আচ্ছা, ইন্টারনেট প্রবলেম হতে পারে। দেখো দেখাচ্ছি, এখন দেখতে পাচ্ছ?
হ্যাঁ স্যার।
হ্যাঁ হ্যাঁ, দেখো আমি আই এম জাস্ট টকিং অ্যাবাউট দ্য ভেরিয়াস বাউন্ডারিজ of these regions. So we have 1, 2, 3, 4 possibilities, and we have talked about the 4 boundaries here. The first boundary is radiation and ideal gas boundary. This we worked out, remember, slope 1/3. You see, this is the slope 1/3 in the log T log rho plot. Again, next, ideal gas and non-relativistic degenerate gas. This one, again you see, slope 2/3. This is the slope 2/3. What about the region between non-relativistic and extreme relativistic case? Remember, we found this relation, constant density line. So this is the region. And then the 4th case, which is basically ideal gas and extreme relativistic case, this region. And we just worked out previously that this belongs to the slope 1/3. So we have talked about the 4 regions or boundaries. Okay, transition regions. Any questions? Okay, so now let me talk about ionization